Alright, 4.5, implicit differentiation. So we've been talking about derivatives all chapter, as you are aware, and the way we've been doing derivatives has always been y equals, that's a terrible y, there we go, y equals something, right? We've been doing derivatives by what would be called explicit differentiation. I'm never going to straight up say you're going to do find a derivative using explicit differentiation, but that's what it's been. It's been y equals blah, 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 whatever that may be. But there are times when you could have a function that isn't necessarily y equals exactly. It could have x plus y squared or whatever. Or something else other than just y by itself, right? In these cases, we could use something to help us find a derivative called implicit differentiation, okay? And whenever we use implicit differentiation, I know I've been saying this can be shown as a derivative, this can be a symbol for a derivative, among many others, okay? But what we are going to be using in order to implicitly differentiate is dy over dx, okay? So make a note of that. We're using this right here, dy over dx. Alright, so we're going to give you some steps to follow in order to implicitly differentiate. Step 1. These are right from your book. They did a great job of outlining what we need to do in order to solve this. Alright, so step 1, differentiate. With respect to x on both sides of the equation. Okay? So you're just going to straight up differentiate, first step. Boom. Differentiate, you're done. Alright, step 2. Move all dy over dx terms to one side of the equation and all others to the opposite side. It's kind of weird saying these steps without actually seeing a problem, but I will be saying these steps out loud to you as we do some examples together, okay? So we'll be fine. 3. Factor. Don't be too scared about hearing factor. You're only going to be factoring dy dx out of one side of the equation. And then finally, last step, solve for dy dx. Right? And those are your full 4 steps. We will do some examples together now. Alright, what was step 1? Here's our first example. Step 1 said differentiate both sides of the equation with respect to x. So, we'll get 3x squared. We are multiplying x and y, so we have to use our favorite product rule. So, the first term is 1, so we just left with 1y plus, keep x the same, but we have a dy dx, because everywhere we differentiate with respect to y, we replace it with dy dx. Plus 2y dy dx. Every time we find a derivative with respect to y, we have to put in dy dx. Equals 0. Okay, derivative 7, any constant is going to be 0. Now, what was step 3? Wait, I kind of skipped step 2, I'm sorry. Step 2, we need to move all the dy dx terms on one side and all the non-dy dx terms to the other. So if I distribute that negative sign, and then we move everything to one side. Everything meaning all the dy dx on one side and a non-dy dx to the other. So I'm going to move the non-dy dx to the other. And then we go to step 3, and that's factor out the dy dx. So we factor it out. Both terms have it, because as we said in step 2, we need to move all the dy dx on one side and all the non-dy dx on the other. We can't factor it out unless that happens. And we did it, and then we factored out. And now, step 4, solve for dy dx. So I just divide by whatever I have in these parentheses. And that is your answer. Dy dx is equal to negative 3x squared plus y divided by negative x plus 2y. Alright, so not only are we going to find dy dx by using implicit differentiation, we're going to find the derivative at the given point, negative 1, 1. So let's get to it. So this left side, we have to use our favorite chain rule. Bring 3 up front, subtract 1 from the exponent, and then multiply by the derivative of the inside. Derivative of the inside will just be 1 plus dy dx equals 3x squared plus 3y squared dy dx. As you are aware, we need to move all the dy dx to one side, but first we need to distribute. So we're going to get 3x plus y all squared plus that same thing dy dx. Because look, hey, we're taking this and multiply by 1 and dy dx. And then left side will keep the same. Now let's move all the dy dx to the left and all the non-dy dx to the right. What's lucky about this, since we're evaluating a point, I don't need to fully simplify, but we do still need to get dy dx alone. So that's going to get us negative 3y squared dy dx plus 3 parentheses xy squared dy dx equals 3x squared minus 3 parentheses x plus y squared. So I factor out dy dx out of both terms. And I'm out of space. So I'll verbalize some things then. So you're just going to take this whole thing right here and divide it by this. Okay? And then you can plug in negative 1 and 1 everywhere you see. And when you do that, just plug in negative 1 and 1 and solve. You will get, it will come out to be negative 1. Okay? So when you plug this in your calculator, be careful plugging in with signs, okay? So maybe do the numerator first and denominator last and divide. But either way, be careful with your signs, please. So we need to find, in this case, as the directions say in your guided notes, the tangent line and the normal line to the circle at a given point. So here's, hopefully you remember from your days of doing conics, the last 2 years of your math life, that this is a circle. So we are going to find the derivative implicitly, and then we're going to find a tangent normal line. Now you might be like, oh, we did tangent line earlier, Sandra, vaguely remember, but what about normal line? Normal line is the perpendicular to the tangent line, okay? So whatever slope we find, we need to just find the opposite reciprocal if it's perpendicular, right? So 2x plus 2y equals 0. So isolate your, well, my bad. I forgot an important part. Dy dx equals 0. Move the 2x over. Subtract equals negative 2x. Divide by 2y. Get dy dx equals negative x over y because the 2's cancel. So slope at 6, 0 is going to be negative 6 over 0. Oh, it doesn't exist. Oh, that makes things interesting. Okay. So therefore, if it doesn't exist, it's undefined slope. For your normal line, it would be flipped, right? So it would be 0. Normal line, slope equals 0. Tangent line equals undefined. Now for the equations, if it's at the point, remember, undefined is always going to be in the form of x equals, so it'll be x equals 6. I'll plug in this form for our normal line. Slope 0, so this whole thing will go to 0, but we'll do it just for fun. And y minus 0 equals 0, which would just be y equals 0 for your normal line. Normal and tangent. Alright, last problem we're going to do together. This time we're going to implicitly differentiate this twice. Okay? And find it in terms of just x and y, that final answer. So we're going to find the first derivative, dy dx, because we found derivative y, equals 0. Move all the dy dx on one side. We're going to just make it positive. I'm just going to move the dy dx to the other side, add it to the other side, and then divide by 2y. 2's cancel, I'm left with x over y equals dy dx. Now I must use quotient rule here. And when we do that, we're going to get y squared on the denominator. We're just going to take care of that. And then it's going to be y times 1 minus x times dy dx. Now we're not done yet. This is when we're doing implicitly differentiating twice. We want it in terms of x and y. So everywhere we see a dy dx, we must substitute anything times 1 is itself. So I'm just going to leave y like that. So I'm going to put in x over y. And then we're going to get y minus x squared over y all over y squared. And then I'm going to rewrite this to make it help us out a little bit. So we're dividing by y squared. I'm just going to do this right here. Dividing by y squared, just like multiplying by 1 over y squared, which will then get us 1 over y minus x squared over y cubed. And that would be our final answer, because I distributed the 1 over y squared to both terms. That's everything. I appreciate you watching, and we'll see you later.